Hi, I'm Ray Raganese, Director of Power Storage Solutions for Licap Technologies. Marty Mills and I will be talking to you today about ultracapacitor principles of operation, construction, and Licap's patented activated dry electrode and its effect on performance characteristics. In this slide, we'll examine the basic model of a traditional capacitor consisting of parallel conductor plates sandwiched between a dielectric material. The dielectric material has a dielectric constant, epsilon. The plates are separated by a distance, d. The standard capacitance formula is capacitance equals the dielectric constant times the area of conductive plates, or electrodes, divided by the distance between the plates. In short, the larger the surface area and the smaller the distance between the charged conductor plates, the higher the capacitance. It seems a bit counterintuitive that a smaller d would yield a higher capacitance, but the smaller distance between the opposite charged plates yields a higher electric field strength, which in turn stores more charge. Okay, you know what a capacitor is. So what's an ultracapacitor? Also known as a supercapacitor or EDLC. An ultracapacitor does not use a dielectric material like traditional capacitors. Instead, it utilizes porous activated carbon electrodes which attract oppositely charged ions from the electrolyte when voltage is applied across the terminals. The electric field is established locally at the carbon particle adsorbed ion interface, thus storing charge. Let's refer back to the capacitance equation. Take a look at the image circled in red at the right. Capacitance is directly proportional to the area and inversely proportional to the distance between the positive and negative charged surfaces. So, an ultracapacitor has an extremely large surface area, a porous carbon matrix, on the order of 3,000 square meters per gram. That's a little more than half a football field in 1 gram of material. That's crazy. So A is very large. Additionally, the charge separation is on the order of the diameter of a single adsorbed ion, 2 to 10 angstroms. So D is extremely small. Using the equation for capacitance, you can now see why ultracapacitors have such a high capacitance value. Let's take a closer look at what's happening at the micro level. The electrolyte solution is comprised of a non-aqueous polarized solvent with solvated positive and negative ions. As seen in the image on the left, when voltage is applied, the positive ions are attracted to the negatively charged carbon electrode surface. A layer of polarized solvent is adsorbed onto the carbon surface, known as the inner Helmholtz layer, and the positive ion is then adsorbed onto the polar solvent layer, known as the outer Helmholtz layer. This establishes the electric double layer in an electric double layer, or EDLC, capacitor, which is more commonly known as an ultracapacitor or supercapacitor. The figure on the left is how you'll generally see the electric double layer concept depicted, but the figure on the right is a more accurate description, as it shows that the activated carbon electrode is actually a highly porous matrix capable of adsorbing ions throughout the bulk of the electrode, not just the surface. This is very different from traditional capacitors whose surfaces are planar. Here we see a cross-sectional view of an ultracapacitor in both the uncharged and charged states. The figure on the left shows the uncharged state, whereby the electrolyte, which is comprised of a non-aqueous polar solvent and both positive and negative ions. As you can see, the positive and negative ions are randomly dispersed on both sides of the semi-permeable separator, as there's no charge to attract them to either surface. The figure on the right shows the charged state. As you can see, when voltage is applied, and the electrodes now exhibit either a positive or negative polarity, the ions cross the semi-permeable separator and line at the oppositely charged electrode surface. Positive ions are attracted to the negative electrode and vice versa. When the ultracap is again discharged, the ions will redistribute randomly in the electrolyte solution. The construction of an ultracapacitor cell isn't much different than a typical cylindrical capacitor. A jelly roll winding consists of layers of carbon electrode aluminum foil current collector laminate, followed by the semi-permeable separator paper and another identical carbon electrode aluminum foil current collector laminate. You can see that on the left. The jelly roll is placed inside the metal can enclosure. Licap uses metal collector discs on both ends of the jelly roll to maximize the electrical conductivity of the current path, or minimizing the contact resistance, one and the same. Not all manufacturers use collector plates in all of their cells, but this is a significant advantage from an ESR standpoint. The jelly roll assembly is placed inside the can, and electrolyte is added prior to sealing the can. Licap uses a hermetic laser welding process for all of their cells, providing the best protection from moisture ingress from the external environment. Some manufacturers utilize different sealing methods. The main properties of interest for an ultracapacitor are capacitance, ESR, and leakage current. In the coming slides, we'll focus on capacitance and ESR, as these properties determine cell lifetime as both degrade over time. We will examine the factors that determine how quickly these properties degrade. Capacitance is important as it determines the amount of stored energy at any given voltage. ESR is important as it determines the power that could be delivered and the degree of internal temperature rise. In turn, temperature is a major determining factor for mean service lifetime of the cell. Leakage current is worth noting as it is also an important factor, but we're limited on time, so we're going to focus on capacitance and ESR. Let's talk about capacitance. Capacitance is a function of the surface area having adsorbed ions and the charge separation between the surface and the ion. As the cell ages, capacitance decreases. End of useful life is defined as a 20% decrease in capacitance. So how does the cell lose capacitance? The main driver is the loss of active surface area for ion adsorption. Temperature and voltage provide the driving force energy for internal reactions that cause organic constituents to dissociate, creating gases as a byproduct of the reactions. In turn, these non-ionic gases adsorb onto the carbon electrode surface, making that area unavailable to store charge. The other mechanism is the mechanical loss of carbon electrode mass into the bulk electrolyte solution. A strong, durable electrode minimizes this effect. ESR, or equivalent series resistance, is the electrical resistance to the flow of electrons from the internal electrodes to the external terminals. It's the net sum of resistances from multiple interfaces, which we will explore in the next slide. As an ultracapacitor cell ages, the ESR increases, creating higher average temperatures and an acceleration of further property degradation. As stated in the previous slide, the temperature and voltage driven reactions cause gas byproducts that are adsorbed onto the surface of the porous carbon electrode, as well as the interface between the bulk electrode and the current collector foil. These gases have low electrical conductivity, or high electrical resistivity, thus increasing overall cell ESR. So here's a look at some of the interfaces where resistance to electron flow contributes to ESR. Location number 1 is the interface between the adsorbed ion and the carbon electrode surface. Maximum conductivity occurs when the carbon and ion have nothing impeding electron flow, but a layer of organic binder or adsorbed gases can inhibit electron flow at this interface. The very same is true for interface number 2, which is the area between the carbon particles within the carbon electrode matrix. Then there's interface number 3, which is the attachment point of the carbon electrode and the current collector foil. At this interface, you actually want a solid, continuous layer of thin binder material to make contact, as any discontinuity or air gap or adsorbed gases will inhibit electron flow more significantly than the binder material itself. Interface number 4 is the connection point between the current collector foil jelly roll and the external terminal. This interface has more to do with cell construction than the type of electrode used. As indicated previously, a robust metal collector disc is far better conductor than a small wire welded to the collector foil, and thus cells constructed with the metal collector discs exhibit lower ESRs. While an ultracapacitor's useful life is defined as a specified amount of degradation of initial capacitance and ESR, there are instances when a cell could fail catastrophically. This results in a cell venting to relieve pressure built up within the cell. As you can see in the figure on the right, a safety vent is built into the can, which is designed to open when the internal pressure reaches a specified value. As discussed earlier, temperature and applied voltage provide the driving force for reactions that result in the evolution of gases. Gases, in turn, increase the internal pressure within the cell. A venting event is usually a result of the cell being used at voltages or temperatures that exceed the specifications. If excess impurities are present within the cell, typically latent solvents or moisture, additional gas byproducts will be produced, increasing internal pressure and making a venting event even more likely. Let me introduce Licap's patented activated dry electrode technology and provide a very basic comparison to the wet slurry electrode manufacturing method used by all other ultracapacitor manufacturers. In very simplistic terms, the main difference is that the activated dry electrode process is completely dry. There are no solvents introduced in the process. Conversely, the wet slurry method begins with creating a slurry, which is a mixture of an organic binder dissolved in an organic solvent, along with the activated carbon particles. This slurry is directly applied to the current collector foil substrate, and the foil electrode laminate is then dried by forced convection. As the solvent is removed from the electrode slurry, there's a net shrinkage that can create residual stresses in the film. Additionally, the drying process is not 100% efficient, resulting in residual solvent impurities remaining in the finished electrode. We'll take a closer look at the Licap activated dry electrode process in the next slide. Licap's patented activated dry electrode technology utilizes proprietary chemistries, equipment, and process methodologies to produce the world's only true dry electrode for use in ultracapacitors and lithium-ion capacitors. The process can also be used for batteries, as it's agnostic to the electrode material chemistry. The process begins with dry binder activation and mixing with the highly characterized carbon particles. Step 1. The dry powder formulation is then rolled into a freestanding electrode that's extremely tough and flexible. As this is a completely dry process, there's no net shrinkage or residual stresses in the freestanding electrode. In the last step, the freestanding electrode is laminated to the current collector foil, providing complete physical continuity at the interface. No air gaps. This is different from the wet method, which utilizes the dissolved binder to adhere to the current collector. The resulting activated dry electrode laminate is extremely tough, durable, and flexible compared with fabricated wet electrode. These photos show the results of a simple comparison of the mechanical integrity of electrodes manufactured with Licap's activated dry electrode and other electrodes manufactured using the wet method. All electrodes were folded 5 times each and examined. As you can see, the dry electrode is more mechanically robust in both the bulk matrix and the important electrode current collector interface. There is no flaking or cracking of the dry electrode compared with the wet processed electrodes. In the following slides, we'll examine other electrode-specific performance factors. As mentioned previously, the wet process uses an organic binder which is dissolved in an organic solvent and subsequently dried. As the drying process is not 100% efficient, residual solvent can be present in the completed wet slurry process electrode. These solvents are impurities that are subject to redox reactions which produce gas byproducts. As we've seen previously, gases adsorbed into the porous carbon electrode matrix lead to both reduced capacitance and increased ESR, and can also contribute to additional internal pressure and a possible venting event, depending on other operating factors, temperature, current, voltage. Additionally, residual solvent and subsequent gas evolution at the electrode current collector interface can cause further degradation to ESR by increasing interfacial contact resistance. Licap's process is completely dry, so there are no residual solvent effects. Drying may seem like a trivial process, but in reality it's quite complex, with many variables affecting performance and yields. I know this firsthand from my background in ceramic engineering. The drying process for wet electrode can lead to an uneven distribution of binder throughout the thickness of the electrode. Basically, there's an accumulation of binder at the surface and a corresponding depletion at the current collector interface. The binder migration phenomenon can lead to increased electrical resistivity, ESR, and/or mechanical failure, such as delamination of the electrode from the current collector foil. Not all processes are created equal, and some will result in less binder migration than others, but the phenomenon exists and cannot be completely avoided in wet electrode manufacturing. Again, Licap has no drying process and therefore no binder migration phenomenon to adversely affect performance. Now let's look at binder dispersion. In a wet electrode, the organic binder is fully dissolved in an organic solvent. During mixing, the binder solution attempts to fully wet the individual carbon particles. Upon drying, a semi-continuous film is created, coating most of the surface of the individual carbon particles, and the binder film essentially sticks to itself, forming the electrode. While this accomplishes the goal of forming a thin electrode with adequate mechanical strength, the binder component has poor electrical conductivity, causing increased electrical resistance at both the ion-carbon interface and between the carbon particles themselves, thus increasing ESR. In the figure on the left, the blue area is the binder shown coating the carbon particles. The resistor symbols show that there is added resistance at the ion-carbon and carbon-carbon interfaces. The figure on the right depicts the Licap activated dry electrode. Unlike the wet process, the activated dry process utilizes well-dispersed dry binder particles, which provide a very strong mechanical bond between the carbon particles, but do not coat the entire surface. This allows for better conductivity at both the ion-carbon and carbon-carbon interfaces, resulting in lower ESR. The Licap dry process also uses less binder, which allows more carbon per unit volume and corresponding higher capacitance. Here's a quick summary of advantages realized by Licap's activated dry electrode. The first two items relate mostly to our customers interested in licensing our technology for their battery manufacturing. In short, the Licap technology can provide lower capex and manufacturing costs for large-scale electrode production. We have previously shown that electrode produced using the activated dry process is far more durable than wet process electrode, resulting in overall improvement in reliability and minimization of capacitance loss. The activated dry process uses no solvent, so there are no issues related to residual solvent. The result is an overall improvement in reliability and better stability versus time for both capacitance and ESR. Lastly, the uniform binder dispersion in the activated dry electrode process allows for both improved initial specifications, capacitance and ESR, and less degradation of those properties versus time and cycling. Here's a summary of Licap cell construction factors that influence real-world performance. Number 1, Licap is the only manufacturer using dry electrode for ultracapacitor and lithium-ion capacitors. The numerous benefits have been outlined in the previous slides. Number 2, the freestanding carbon electrode, unique to Licap's activated dry process, allows for the most mechanically durable electrode current collector laminate structure and the best interfacial resistance, which results in superior ESR. Number 3, the use of metal collector plates versus welded wire leads further lowers contact resistance, resulting in lower ESR. And lastly, the use of laser welded hermetic enclosures ensures that there is no ingress of moisture or other contaminants that could deleteriously affect performance characteristics.
Thank you, Ray. Well done. That was an excellent overview of our activated dry electrode technology. Hello everyone, my name is Marty Mills. I'm the VP of Sales for Licap Technologies. Now I'd like to talk to you about two of our product lines that we have utilizing our activated dry electrode. We have EDLCs, or also known as Ultracaps or Supercaps, as Ray mentioned, and then we also have a product line of lithium-ion capacitors. Let's compare the two. Nominal voltage range for an EDLC is 2.7 to 3 volts in our product line. In the LIC, it's maximum 3.8 volts, and we go to a minimum of 2.2 volts. The energy density in this particular case, and the cells shown, is 5.1 watt-hours per kilogram versus 13.4 watt-hours per kilogram, roughly 2.5 to 3 times the energy density. The energy storage is electrostatic in an EDLC and electrochemical for LICs. Both use activated carbon, and on the lithium capacitor, it's doped with lithium ions. Internal resistance is still very low for both cases, and we can get up to 1 million charge-discharge cycles out of a traditional EDLC and 500,000 on an LIC, which is still very impressive. Calendar life is 10 years for both, and temperature range is -40 to +65 on an EDLC and -10 to +70 C on an LIC. Now let's talk about our EDLC or ultracapacitor cell product line. In the top row, we have our D family size series of cells ranging from 350 farad 2.7 volt, 370 farad 2.7 volt, 370 farad 3 volt, and 600 farad 2.85 volt cells. In our larger family of cells, we have 1200 farad 2.7 volt, 3000 farad 2.7 volt, and 3000 farad 3 volt, our newest cell. These cells all are available in the modules that we'll talk about next. Now let's talk about our module product family. In the upper left-hand corner, you can see 4 modules ranging from 16 volts to 18 volts using the same housing. These all use a variety of the different D-size cells that we showed on the previous slide. The 15 volt and 17 volt do not have any passive balancing resistors. That's why we have to derate the voltage some. Similarly, in the 160 to 180 volt modules below, we also have no balance options available. In the upper middle, we have a 16 volt 500 farad module that uses 3000 farad 2.7 volt cells. And down below in the middle, we also have a specialized 16 volt 500 farad modules dedicated to our wind retrofit applications for GE turbines. In the upper right, we have a 48 volt 165 farad module that uses the 3000 2.7 volt cells, and also a 54 volt module 165 farad that uses the 3000 farad 3 volt cells. And last but not least, we have a 64 volt 125 farad module that's dedicated for rack mount applications and stationary applications for the grid. Now we'll look at Licap's lithium-ion capacitor cells that are in pilot production and currently 100% made in Sacramento, California. The first is a 200 farad 3.8 volt LIC cell in an 18650 form factor, and the second is an 800 farad 3.8 volt LIC cell in a 32650 form factor. Samples are available for purchase now, and you can let us know if you're interested in doing some testing. In summary, you can get more information by visiting us at www.lecaptech.com. We have more information and details available about our EDLC or ultracapacitor cells and modules, our lithium-ion capacitor cells, and also our activated dry electrode technology. Lastly, I'd like to thank all of you for your time today, and hopefully you've learned something new. I'd also like to thank Richardson RFPD for the invitation to participate in this event. Please feel free to reach out to your local RFPD representative if you'd like more details or technical information from us. Thank you. Have a great day.